questions for equations with interaction on manifolds. Please.
Thank you very much for the introduction. And let me, before I begin with the whole topic, quickly recall what the Krylov-Veretennikov expansion actually was. So we have the following situation. We look at normal SDE. By the way, can you see my mouse when I do?
Yes.
Okay, good. We look at the normal SDE, or a system of SDEs for each initial condition with Lipschitz coefficients with at most linear growth, one dimension, and we also assume B to be non-degenerate. Then Krylov and Veretennikov have proven that the E to Wiener expansion of test function, in this case, bounded and measurable function from R to R, applied to the solution of this SDE is equal to, the semigroup plus the E to Wiener kernels of higher degree or of higher order can be explicitly written down in this form, where we have, iteratively the semigroup applied to the function, then we differentiate this, multiply by B, and so on and so on. So we have this special decomposition, which only depends on the data of the equation, which would be the initial condition, the semigroup, and the coefficient B. So this is the only thing that the E to Wiener expansion does, in this case, does depend on, and actually should, because, there should be a nice E to Wiener expansion depending on the initial data. And we try to do a similar thing, but for something a bit more complicated. We try to do it for to apply it onto a measure value process induced by an SDE with interaction. And the broader area that we wanted to cover was investigation of ergodicity of the measure value process, which is induced by SDEs with interaction on compact manifolds, because this would be a Markov process. Sorry, I will turn off my sound. This would be a Markov process on the Wasserstein space over a compact manifold, a compact Riemannian manifold, and the Wasserstein space over a separable compact space is always itself compact. So by the Krylov-Bogolyubov theorem, one would always have an invariant measure and could start investing ergodicity. But the usual techniques which are applied in ergodicity theory have failed in our investigation. Oh, by the way, I forgot to mention this is based on work in progress together with Andrei Anatolievich Dargovtsev for my PhD thesis. Yeah, sorry. The typical techniques failed, and therefore we have started to look for maybe partial ergodicity results, which don't cover ergodicity maybe for the entire measure value process, but maybe just for the E to Wiener kernels of functionals of the measure value process. And in order to investigate E to Wiener kernels of the E to Wiener expansion, we would like to have them a good form. And this is why we started to investigate the Krylov-Veretennikov expansion for these kind of processes. And let me quickly tell you how we, or what the main ingredients are in order to get such Krylov-Veretennikov expansion. And for this, I want to quote or cite a paper by Andrei Anatolievich, where he has generalized the result of Krylov and Veretennikov for general on general real separable Hilbert spaces. And for this, let me quickly give some definitions so you will understand the final result. So H should be a real separable Hilbert space, and Xi should be Gaussian white noise on H times L2 from 0 to infinity. Then we have a family of random operators, GST, and these are called multiplicative functionals if GST is measurable with respect to the filtration which is induced by the increments of this Gaussian white noise. GSS should be the identity, and we have such a flow property, so to say. In general, applying strong random operators to strong random operators doesn't give a random operator in the sense as a linear and continuous operator, because they're those operators are not pointwise or omega-wise operators, but rather seen as a random function. But since GS2 and SR and S1 and S2 are independent from one another because it depends on the increments of the Gaussian white noise, a measurable modification can be made sense of in this case. Okay, so then let me introduce the following operator, which would be this limit of this random family of strong random operators, which would just be as in the beginning just the function applied to the solution of the SDE. This is the family of strong random operators in that example. And then we have this scalar product here of Xi and H just until time t. This is just a normal multiplication. So we work here on R. And as I mentioned, so one can make sense of this with this example that we heard earlier. If we look at the Hilbert space L2 of R and look at the strong random operator being a test function or an L2 function applied to the process, in this case, the operator AF is B times, or well, the operator A. So sorry for the typo. The operator A is our the diffusion coefficient times differentiation. And so from this we can already see that this is not applicable to all functions f, but only to C2 functions, because actually in order to prove this, one has to apply Ito's formula. And then one can see that the operator A must be of this kind. And if we look closely, this operator A is actually what we have in the Krylov-Veretennikov expansion. So it is one of the things that the E2-Wiener expansion depends on, which comes from the solution. And now we finally come to the general result proven by Andrei Anatolievich. And the theorem states the following. So let the semigroups of H, so TT of H, be in the domain of the operator for all T. And also the kernels of the Wiener E2-Wiener decomposition should be continuous in time. Then we have such a expansion, the generalized Krylov-Veretennikov expansion of E2-Wiener kernels. And we actually want to apply the same technique of proof the same proof as in this theorem. And for this, we need a couple of ingredients. So firstly, we need to have some conditions such that the semigroup applied to our space is in the domain of our operator. Since this is a differential operator, in general, this is something like a smoothing property. In our case, we will only look at already smooth test objects. And then the second thing is to show the continuity in time of the E2 Wiener kernels, which is something one can do with the help of Malliavin Calculus. But yeah, without further ado, let me start to present to you the procedure of how we want to achieve a Krylov-Veretennikov expansion and what it should look like, especially what a differential operator like A would look like on the space of on the Wasserstein space. And yeah, before we start, let me fix some notation. So first of all, let M be a compact, connected, d-dimensional Riemannian manifold. So since it's Riemannian, it's smooth, and it has a Riemannian metric on the tangent space. Then we need to look, since we look at an SDE with interaction, our vector fields which drive our SDE should also depend on the Wasserstein space. And therefore, we will denote this space of infinity alpha functions. Here I have forgotten, I'm sorry, the tangent bundle, but it's functions which go from M times the Wasserstein space into the tangent bundle in the following way. So yeah, these are the types of functions we look at. And for each fixed mu, the function from M to the tangent bundle is a smooth vector field. And for each fixed x, the function from the Wasserstein space into the tangent space at x should be alpha Hölder continuous for all x in M. And this can actually be made sense of because if, as we remember, maybe each tangent space is a Euclidean space, or moreover, a Hilbert space of the same dimension as our initial space. Therefore, we also have a norm. It's a normed space, so we can actually make sense of alpha Hölder continuity. Okay, yes. Before we introduce the general SDEs with interaction, let me first introduce you to the Bonita style SDEs on manifolds. And well, for this, we have here this space here. This is the space of all smooth vector fields on M. And a stochastic process Ft with values in the space is called a continuous semi-martingale, well, with values in the space, if and only if the application of a smooth function to this, yeah, to this vector field is a continuous smooth function, or is first of all almost surely a continuous smooth function, and moreover, it is a continuous stochastic process, or more general, semi-martingale. An example for these kind of, a very easy example for these kind of smooth vector field valued semi-martingales is the following. Let us look at some vector fields Vi. So sorry, here I forgot. This is not a smooth function. This is a typo. This should be a vector field, so it maps from M to the tangent bundle. And let Bti be independent Brownian motions. Then the following object here, where the Brownian motions are one-dimensional, is a continuous gamma Tm semi-martingale. Okay, so what do we need this for? We want to look at Kunita-style SDEs. In particular, we want to look at SDEs with interaction. And a system of SDEs with interaction on a manifold will be considered in the following way. So let this be our vector fields, which are smooth with respect to the manifold component, and Lipschitz with respect to the Wasserstein component. And let's look at independent Brownian motions. Then a solution to a solution to the system or the differential equation is denoted as following. dxut is equal to integration with respect to the semi-martingale in Kunita style. But here we have the Statonovich integral. And each particle starts at some point u and m. And then we have a special form of this driving semi-martingale f. It should look like this. So in a sense, if you look at this, it looks like first you have to solve the system with interaction, and then only you can look at actually look at this equation, because only then you have the corresponding semi-martingale. But this is exactly what you could do in the RD case as well, in the general case, where you can solve the equation, then you can fix the measure value process and look at the semi-martingale. And with the help of this semi-martingale, you could rewrite the system with interaction into a Kunita style SDE. And we have, while we just use this on manifolds as a definition. And let me quickly introduce to you what the definition of a solution is to be. So the definitions are with the help of test functions. So a continuous adaptive stochastic process with values in M is a solution to the stochastic differential equation if for all test functions f, which are C infinity functions mapping to R, we have this integral equation, where here we apply this where we apply the vector field valued semi-martingale to our function f. And this for all u and m. If this holds, then we have a solution. And then before we start with an existence result, let me state a very important result in the theory of differential geometry. And this is the so-called Nash embedding. So the result is the following. Whenever we have a smooth Riemannian manifold, M, there exists some natural number such that there exists a smooth and proper and isometric embedding of our manifold M into the space R to the n. So we could, in general, consider every manifold as a submanifold of some Rn. But something very important here is each Riemannian metric induces a geodesic distance on Riemannian manifolds. And the isometry, which is mentioned here, does not preserve the isometry, is not the isometry between the geodesic distance on M and the Euclidean distance on Rn, but is much rather an isometry between the Riemannian metric on the tangent space and the normal inner product on Rn. So, yeah.
Alexander,
Yes.
I just forgot. Can we control the dimension can we control this n capital? Because I remember something like if dimension m is d, then we have n like 2d plus something, yeah, or not?
Yeah, there is something, I don't know the exact number. I think it's something like 2 times d plus 1,
Oh, I see. I see.
something
Mhm.
like that. But
So, so we can do that, but
yes,
it is
there
not
is.
necessary, yeah?
Yes,
Okay.
it is not necessary for our considerations. There is a control of this number n. The better your manifold, the better the control is, but we don't care in our investigations. Yes, but this is an important result. This is, for example, proven by John Nash, hence the name Nash embedding. But there are many, many authors proving more general results or versions of it. So it is a classical result, I would say. Okay, then let's get to the existence and uniqueness theorem. So we consider our equation with interactions where we have our vector fields vi, and we have this v tilde 0. The tilde comes from the fact that we have a Statonovich integral. So this v tilde is the initial v0 plus the Statonovich correction, which cannot be written down coordinate free. So writing it down always depends on the coordinate, but it can be made sense of as a vector field. So this vector field exists, and we can control it. Sorry, and they should be in the space of infinity 1. Again, it should be vector fields, not smooth functions into R. I'm sorry for the typo. Then if we have this condition, so Lipschitz with respect to Wasserstein and smooth with respect to our manifold, then there exists a unique solution to the SDEs with interaction, a unique strong solution. And in order to show this, the idea is the following. We embed the equation into Rn. So this is there are two ways how to prove uniqueness and existence for SDEs on manifolds. One way is via coordinates, but this is I don't think this is the right way in our case. And another way is by embedding the equation into Rn, enlarge the vector fields, in our case smoothly, and we can also enlarge them Lipschitz with respect to the measure variable, because we use not just an embedding, but an isometric embedding. So the Lipschitz property is actually preserved for any enlargement that we look at, or for any embedded vector field that we look at. And after we have embedded it, we can just apply the usual techniques of Picard iterations, which has been shown, for example, by Andrei Anatольevich in his book, in order to show, well, posedness. Another, maybe important remark is that due to compactness, the geodesic distance and the Euclidean distance can actually be estimated. So we can estimate the geodesic distance by the Euclidean distance from above and from below. So we really have that this isometric embedding is not only an isometric embedding in terms of the Riemannian metric, but it is also B Lipschitz in terms of looking as a map from a manifold into Rn, or from a metric space into Rn. Therefore, we can do the exact same procedures or very similar procedures as in Andrei Anatolievich's book. Okay. Yeah. Then, after we have discussed the existence and uniqueness, we will now come back to the Krylov-Veretennikov expansion. And more precisely, what we want to expand is the R-valued random variable f mu t, where f is a sufficiently smooth function, which I will later explain what that actually means, but they map from the Wasserstein space into R. And well, we want to have an expansion just like I have written down here without, well, first, we don't know what our operators A should look like, but they should look like something. Note that in this Krylov-Veretennikov expansion, we have actually the the indices here in the semigroup, we have them flipped in here. I don't know, simply because this is the only thing that we are at the moment able to prove with these flipped indices, simply because in the proof of Andrei Anatolievich's results, he heavily relies on linearity of the Hilbert space, the linear structure of the Hilbert space, which allows him to flip stuff in the E to Wiener expansion as he wants. But in our case here, we cannot do this, so we will first only have this kind of expansion. But yeah, well, we have a direct expansion which only depends on, well, which only should depend on our initial data and the coefficients and the semigroup induced by our Markov process. Okay, so we can actually make an educated guess what our A or AI should be. They should just be the limit of these kind of expectations. And if you remember my comment earlier, where I said that the concrete form of this A can be computed via the E2 formula, we will be actually able to do the same here. But for this, we need to talk about smoothness with respect to the Wasserstein space and prove an E2 formula for the measure value process. And let me do this by introducing the concept of intrinsic differentiability or intrinsic differentiation of functionals from the Wasserstein space. Let's consider, let V be in the set of smooth vector fields, and we denote the flow generated from V by phi V T dot. So what is the flow generated from V? Just very quickly, this is just the solution to the ODE, where the vector field V is the coefficient of this ODE. And then, yeah, just like in RD, there is a flow coming from that, and we denote this flow by phi at point T from V. And then the definition of intrinsic differentiability for functionals from the Wasserstein space to R is the following. So the function is called intrinsically differentiable if for all smooth V, the following limit here exists. Sorry, I have a sore throat today, so I need to drink regularly. I apologize for this. We just look at the differential quotient of our function evaluated at mu push forwarded with respect to the flow. At time epsilon, and then yeah, well, just the difference quotient of these of this entity. And if this exists for all V, and if the resulting object is continuous with respect to L2 Tm mu, then it is called intrinsically differentiable. Furthermore, if it is continuous with respect to L2, we can enlarge this map div into not only for smooth functions, but for all functions in L2. And by the Ries-Fischer theorem, there also exists a function such that the intrinsic derivative can be written as a scalar product of a L2 function times the times the vector field integrated with respect to mu. This will be the notion of differentiability which we will use. If you maybe remember other talks in the seminar, also given by me, this is a different notion for differentiation of Wasserstein functionals than we usually do, which would be the Lyon's differentiation. And I would like to quickly emphasize differences of these two notions. So the definition for the Lyon's derivative is very similar, but instead of the flow, we only use we use the exponential map on the manifold. If you don't know what it is, just imagine it to be the matrix exponential for maybe some matrix manifold matrix Lie group. And on RD, the exponential map is just the identity plus whatever is written down here. So this would be the map x plus epsilon times v. And this is exactly the definition, this is exactly the form of the Lyon's derivative. And we also have this, we can define this here on manifolds. An additional structure which we want the Lyon's derivative to have is this form of, this should be, so this limit should be 0. And so this should be kind of like a Fréchet derivative, so a strong derivative, where this only is a directional derivative. In general, the definitions are pretty similar. If we only look at the directional derivative, we do actually, with this intrinsic derivative, differentiate with respect to into the same direction of this vector field V.
I'm sorry, and the norm of V is L2 norm?
It is the L2 norm, yes. It is the L2 norm, sorry. I forgot to write that down. But it is the L2 norm on the manifold. So instead of
L2 norm in with respect to measure mu, yes?
Yes, exactly, yes. Sorry for not writing this down.
But V may be very non-smooth.
Yes. V may be non-smooth. This is one advantage of the Lyon's derivative, that you can actually look at this difference quotient for very non-smooth functions. All we need is a function which maps from M to our tangent bundle. So it doesn't have to be smooth. And it doesn't even have to be defined everywhere. It can be defined mu almost everywhere because we only look at the push forward in the definition. Does that answer your question?
Explain this derivative. For example, if manifold is just Euclidean space, because
Yes.
I don't understand these non-smooth vector fields.
Okay, let me write it down. So if we have RD, then sorry, wait, I'm not writing. Do you see me writing?
Yes.
Yeah.
Okay, so we look at V in L2 from Rn, to Rn mu. Then this derivative here, here we have the identity plus epsilon V. Minus f of mu divided by epsilon. Limit epsilon to 0. Because on the Euclidean space, the exponential map is just x plus v. Does this answer your question?
Mm,
Can you read this?
yes, I can read,
Okay.
but it's all the same. So epsilon goes to 0 or V goes to 0?
Epsilon. So here epsilon goes to 0.
Mhm.
And then afterwards, in order to call it Lyon's differentiable, so we already have all these Lyon's derivatives here for mu and all V. And then we also look at the difference, then we look at this Fréchet type of limit. Here should be a 0. And this is L2 mu. So this is the directional derivative up here. And then because Lyons was looking at Fréchet differentiability in his work of mean field games, therefore this, this is an additional part of a definition for the actual Lyons derivative as in his books or book. Is everything clear? Or may I continue? Hello?
Andrei, do you hear?
Yes.
Oh, sorry.
Okay. Yes.
Oh, okay, I can. Okay.
Mhm.
Okay, so I hope, yeah, but this is not the notion we will use because, well, the flow notion seems to be more natural for on manifolds, and moreover, we always work with embeddings into Rn. And for example, one can naturally embed with an isometric embedding, one can naturally embed the flow of some vector field into Rn, but it is harder to do this with the exponential function. But in general, they give the same notion, well, a very similar notion for directional derivative, and for all the main examples, they coincide, the directional derivatives do. So it is enough for our considerations. Okay, so I don't know why I can't. Oh, okay, I can delete this now. Okay. So let me just continue with a classical example where we have a function mapping from the manifold to R. And our functional would be just this integral. Oh, I'm sorry, this should be an M, not a T. So this is the integral over M. This is intrinsically differentiable, and one can directly compute this directional derivative. It's just the gradient of f in the scalar product with the vector field v, or one can write it in terms of derivations, where we just apply our vector field v to the function f and integrate it with respect to mu dx. Okay, then this was the definition of intrinsic differentiation. Then let me quickly emphasize that we encounter different functionals from measures which have different images. Therefore, it's important to mention, that there are different definitions. For example, if we have a map from the Wasserstein space to our manifold, then f is intrinsically differentiable if and only if this difference quotient exists, and it would be then in the tangent space of f of mu of m. And it should also be continuous with respect to L2 mu. And a similar definition can also be deduced for actual vector fields that we will have to look at, which map from M times the Wasserstein space into the tangent bundle. But yeah, well, as a introducing example, this definition should always be kept in mind. Okay, and let me also introduce some notation. So one can also define higher order differentials, which we will define like this. Just the nth derivative evaluated at epsilon equal to 0. And we will denote by C infinity n alpha the space of vector fields which are smooth with respect to M or with respect to the spatial variable and n times intrinsically differentiable, such that all derivatives are alpha Hölder continuous with respect to the Wasserstein distance and the geodesic distance as well, where we, what do we mean by the geodesic distance? Well, if we look at what we have written down here, that not only is, well, this is not the only thing that is the intrinsic differential, but we also have this function, and we assume also some smoothness of functions of the functions on these functions when we talk about smoothness of the intrinsic derivatives. So this should also be smooth with respect to the spatial variable and Lipschitz with respect to the measure variable. Yes, because such functions can also be derived in the case of intrinsic differentiation for vector fields. Yeah, but it is, you can just think about it like these functionals that come on from R. It's not a lot more complicated, but I just don't want to write this down. Then, in order to prove our or many of our results, let me mention that whenever we have such a function which is C2 with respect to the Wasserstein space, we can actually look at this function if we only plug in a discrete measure as a function from the product space of M. And whenever it is differentiable, well, intrinsically differentiable, then it is also, oh, sorry, this shouldn't be a 2, it should be an n here. Then it is also differentiable in the usual sense, and we have the following formula. So the nth derivative, intrinsic derivative with into the direction of some vector field at mu m is just, well, yeah, applying the vector field n times to our function f, which results, which is the exchangeable function f tilde, which is the exchangeable function identified with f on the set of discrete measures. And this lemma is important because we will, well, if we want to prove anything, for the measure value process, we will first do it for discrete measures where we can use usual Ito formulas, and then go to the limit and prove it for arbitrary probability measures. And this is also exactly how we prove the Ito formula for our functionals. So we look at these smooth functions and at the measure value process, mu t, induced by the SDs with interaction. Then we have the following Ito formula, which would be, yeah, just f of mu, plus here we just have the intrinsic derivative into direction v0. And here, because our vector fields also depend on the measure, we have up here also a measure component in the vector field. And well, yeah. Then here we have the martingale part and the part which comes from the Ito correction, which is very conveniently just the second order intrinsic derivative of f into the direction of the vi, well, and the sum of them. And the idea to prove this formula, I have already mentioned. Well, we prove it for discrete measures and then we approximate. Yes, and well, with the help of this, we can then compute the operator we were looking for. Yeah, this is just an easy computation, follows immediately from the Ito formula. So I'm not going to emphasize on it anymore. And we will now come to the other ingredients that we need to prove, which would be, first of all, if you remember, let me go quickly back just to recall. The first ingredient would be to show something like this, therefore showing smoothness of the semigroup, which we will show by smoothness of the actual solution, and then also the continuity of the Ito-Wiener kernels. And before we can do this, let me define another class of vector fields, because we cannot, or well, we couldn't prove the smoothness of the solution with respect to the measure variable for very general vector fields, but only such vector fields which are of this form. So we consider the Nash embedding and a vector field which is yeah, smooth and with respect to the to the Wasserstein variable and with respect to the manifold, and it's called smoothly embeddable with respect to the measure component. So, well, we want it to be smoothly embeddable in general, but if you would just call it smoothly embeddable, then people would, yeah, just think that you want to embed it smoothly into the submanifold, but we actually want the smoothness also, the smooth embedding also want with respect to the measure variable in Rn. So it is called like this if there exists an extension like this, such that evaluating it at m, p to m, or well, more precisely would be iota of m. And this space would be the measures on Rn, the probability measures on Rn, which have support in the manifold of iota m. Yes, so basically they coincide where we want them to coincide, and V tilde should inherit the same smoothness properties as we had before. Then it is called smoothly embeddable, and only for these kind of vector fields we will be able to prove smoothness of the solution with respect to the measure variable. Before I continue, let me give an example on how to construct this. So we look at the following vector field here. Yeah, F is smooth on the product manifold, and then we only differentiate with respect to one component. This functional or this vector field has this property of being smoothly embeddable. And the idea how to show this is to enlarge the function to not only to be from our manifold, but enlarge it to the entire Rn times Rn, and then look at this functional. And then, since the smooth structure is carried over from the by the Nash embedding, this function just coincides whenever we plug in a mu, which is supported on our manifold, and yeah, and evaluated at some point in the manifold. So this function has the properties, and there are many more good examples. The most important example, well, this definition works for all the most important examples, but we couldn't prove a general result of smoothly embedding with respect to the intrinsic differentiation. Therefore, we had to work with this workaround definition. And yes, another very important result that we need in order to prove, in order to prove smoothness of the solution to an SDE with interaction with respect to the measure component will be the chain rule, which is the following. We have some functional. For simplicity, I've written down here R, but you can also look at Rn, for example, which is the space we would need the chain rule in the proof for. And we look at a function from some interval I times m into m, such that x and x dot, which is the time derivative of x, are continuous with respect to, well, time and space. Then the function does suffice such a chain rule. Yeah, well, it is just more or less the general chain rule. We have here the derivative of what we have in the inside, and here we have the outer derivative in a sense. But then, yeah, well, since we have functionals from the Wasserstein space, we also integrated with respect to a measure. Okay, and this chain rule now is essential in order to prove the smoothness with respect to the measure component. So we look, what we assume is we want our vector fields to be smooth in both components actually, because we will probably need this later. And they need to be smoothly extendable onto the entire Rn. So not only with respect to the spatial variable, but also to the Wasserstein variable. Then the intrinsic derivative of our solution exists for all smooth vector fields phi, and it solves such a differential equation on the tangent bundle. So yeah, it depends on the gradient and on the intrinsic derivatives of our vector fields, and moreover also, well, on the gradient of our stochastic flow, and as it should be, also on the intrinsic derivative itself. The proof is pretty, well, not simple, but the ingredients for the proof were already there. We embed our equation into Rn and show the theorem there, because there were already previous results. There are results, for example, from Delarue and from Fengyu Wang, which prove smoothness with respect to measure components for such SDEs or for similar SDEs. So the ingredients were already there. We prove it for these enlarged vector fields, and then we transfer it back. And the differentiation, or better said, the intrinsic differentiation actually commutes with this embedding, because we can embed the flow, which is important in the definition of the intrinsic derivative, in a natural way into Rn. So we don't destroy any structure. This is why we have also chosen this intrinsic differential instead of the Lyon's differential, because we cannot really naturally embed this in Lyon's differentiability into Rn from the manifold, because the exponential map is not really transferable. in this natural way. So if you remember, this is our first ingredient. We need smoothness of our solution. Then the second ingredient is the continuity of the E2 Wiener kernels. And here we can, also show, this one can show with the help of Malliavin calculus. For this, we need to we need to compute Malliavin derivatives for our solutions. If you remember my last talk, we have already, where I've already shown this in the case of Rn, but since the Malliavin derivative is only the derivative with respect to the Brownian motion, we have no problems here. And we can just do it in exactly the same way as there. After we embed the equation again into Rn. And then, the Malliavin derivative solves this equation here, where we have the usual part which comes from the chain rule. And then here we also have a part which comes from a chain rule for functionals of the Wasserstein space, which is this lemma here. Which gives us a formula for chain rule for Wasserstein functionals, and this can be proven by, again, proving it for discrete measures and then approximate. Yes. So more or less, we would have all the ingredients. Here I quickly show why the Malliavin derivative leads us to continuity of the E2 Wiener kernels. So if we look at the E2 Wiener expansion, how much time do I have? Oh, I should already, okay, I should already finish. Well then, if we look at the kernels of the E2 Wiener expansion, then for example, for the first kernel, we can integrate it with respect to functions of h. This is just the expectation of our functional. Sorry, this should be small f's here, times this integral here, and then by using the integration by parts formula, we can see how the Malliavin derivative and continuity of the Malliavin derivative is connected to continuity of our E2 Wiener expansion, because this is just this, where di denotes the Malliavin derivative into the direction of only one Brownian motion. Okay. Well, then let's prove, or let me talk about the theorem that is actually in progress. We couldn't fully wrap up all the arguments yet. But if we have, the statement should be the following. If we have smooth functionals of the Wasserstein space and the driving vector fields of the SDE with interactions are smooth with respect to any component, then, and are smoothly embeddable, then we have such an E2 Wiener decomposition, which would be the Krylov-Veretennikov expansion, or actually, well, it would be if we would swap all the semi-groups, but as I said, we cannot reproduce this argument due to the lack of linearity on the Wasserstein space. Why is it in progress? Because I have talked about it like everything has been proven. So in order to achieve sorry, I'm very sorry. So in order for this to make sense, we need actually smoothness of with respect to our initial measure, not only like the first order different intrinsic derivative of the solution of the SDE with respect to the measure component should exist, but it should be infinitely often intrinsically differentiable, because here with rising k, one has more and more derivatives coming up. with respect to the measure. So this has not been proven yet. Therefore, yeah, this is just a theorem in progress. But the proof should, if this problem or this obstacle is solved, then the proof should work in exactly the same way as in Andrei Anatolievich's book, but paper, sorry. The Krylov-Veretennikov expansion for coalescing stochastic flows, where he proves this result. But unfortunately, I see I have run out of time, so yeah, I guess I cannot explain the proof or the idea of the proof. I'm sorry for this. Yeah, well, then thank you for your attention. And this is, oh, sorry. This is all.
Okay, thank you very much. I think that this technical problem, of course, will be overcome.
Yes, I think so.
By the way, it is very closely connected with our idea to study partial ergodicity because, as you remember, the differentiability and smoothness of the semigroup is the first step in obtaining even some estimation for ergodicity. Okay, maybe somebody
Yes,
have
true.
questions or comments, please. Let me do some comments. I think that it will be interesting to consider partial cases related to special group, special manifold. We already have here a lot of talks of Alexei Rudenko about Brownian motion on Carnot group. Carnot group is a special case of the manifold. Why not? And even for Brownian motion itself on Carnot group, it will be good to consider Krylov-Veretennikov expansion, compare it with the changed research formula, and see what happened. By the way, I remember that you get the changed research formula for equation with interaction. Am I right?
On our end, yeah.
Okay, so it will be good to compare it with it because they are very close. Okay, this is what I wanted to comment. Maybe other comments or questions, please. If not, then thank you again for your talk. And as far as I remember, Georgi, maybe I will be, me will be next speaker. Yes.
Yes.
Okay, I will speak about the process of white noises in Hilbert space related to some stochastic semigroups. Okay, then for today that's all. Thanks everybody and see you next week. Bye.
Goodbye.
Thank
Thank
you.
you.
Bye.
Bye.
Bye.